Today we have Dr. Ramesh Vellore sir as a speaker of our first lecture, so that is basics of climate science. I would like to request Shri Savai Sajja sir to kindly introduce Dr. Ramesh Vellore sir to our participants. Sir.
Thank you, Dr. Chetna Madam. Dear participants, I am very happy and honored to introduce today's speaker, Dr. Ramesh Vellore. He has been working as a senior lecture scientist at the Center for Climate Research, Indian Institute of Tropical Meteorology, Pune, since 2011. After the postdoctoral experience from the Desert Research Institute, Reno, Nevada, USA. His research interests rest on extreme weather, climate events, extreme precipitation events, western disturbances, dust storms, and widespread fog are to name a few. His current research interests broadly include large-scale monsoon dynamics, tropical polar circulation interactions, multi-scale dynamics associated with extreme weather episodes in the Himalayan region, dynamics associated with the water vapor distribution in the lower stratosphere during monsoon convection, global and regional scale modeling to address weather and climate phenomena, climate change science, partitioning of global and anthropogenic climate change components to address the climate change impacts on high impact weather events. He has published 44 publications, including 3 book chapters in peer-reviewed journals on the aforementioned themes. His recent book chapter addresses on extreme storms, published in the Assessment of Climate Change over the Indian region, edited by Dr. Krishnan et al. 2020 and unreliving climate change in the Hindu Kush Himalaya, rapid warming in the mountains and increasing extremes, published in the Hindu Kush Himalaya Assessment, Mountain Climate Change, Sustainability and People, edited by Wester et al. 2019. I now request Dr. Vellore sir to start his lecture, and to the participants, they may be they should feel free, and they should ask questions in the chat box, and anytime email addresses are given, so you can stop in between also. So Dr. Vellore sir, start.
Yeah, I'm quite aware. Let me share. I'm kind of new to all these things. So, okay, share.
There is a share button at the bottom.
Are you able to see that?
Presentation mode, sir. Please make it in presentation.
Presentation mode. Okay, so this is the presentation mode.
Yes, yes,
Correct?
sir. We can now we can hear.
Okay. I'm a very face-to-face kind of person, so these are all sometimes confuses me. Okay. Anyway, before that, Gauri, Swapna was asking me. She just called me that she also looking for the link. Did you send?
Same link I have sent to both of you.
Yeah, the same.
On the
Yeah,
email
no, I
address.
mean, like she was worrying, like whether it's the same link, password, that meeting name, everything. Okay. Anyway, you can just resend it if you have time.
Okay,
Right.
sir.
So
Okay.
the topic given to me, it's an elementary thing. So it is kind of basics of climate science, and also followed by another talk like the basics of science behind the climate change. So there could be some redundancy between this because climate science includes climate change. So I mean, like I will try to go as much as I mean, like to give you the elementary details, and followed by Swapna. She will be giving whatever the missing or maybe some redundancy. You got to bear with it. My name is Ramesh Vellore. The Gauri introduced me, and 1 minute. How to go to the next slide? Okay. All right. So before opening the talk, so let's be clear with the the terminology that is being used. Weather is one term, climate is one term, and of course, climate variability is another one. And climate change comes at the end. I mean, like it is also all the climate derivatives. So weather is, as we know, that whether on a particular day at a particular location, okay, the weather is kind of fine. So it is on a daily basis or a few days basis. If you want to talk about it, is called weather. There is nothing called. So many people used to say that today's climate is good. That is absolutely wrong. You have to use today's weather is good or today's weather is bad. The climate, when we come into that, it is kind of an average of all for a long, like on a seasonal scale. If you want to say, okay, this season it's going to be warm as compared to the last season, something like that. It is a compilation of all the weather events, and you say that on an average of all the weather episodes for a longer time, substantially longer time. So that is called climate. So this is the distinction between weather and climate. So let's get into that, the derivatives of climate. So another one is the climate variability, like how the climate varies from one time to other or one season to other. So it could be because of natural variations, such as some coupled atmosphere ocean phenomena like El Nino, like which has a periodicity of 4 to 5 years. So these are all like even the volcanoes. They're all infrequent, so they come and go. So they all come under the natural. So these kind of the forcing is kind of naturally forced. The the atmosphere, how the climate varies in response to that. So that is what refers to the climate variability. Sometimes it is simply referred as natural variability, and followed by the climate change. So the climate change, well, the climate itself is changing. Look, but the normal climate that you expect, it's by itself is changing because of some kind of natural forcing as well as some man-made forcing, like how the climate on a long-term state, how it is going to be changing. So this is a clear distinction between. Do you see the cursor? Uh, uh, Anybody can say that?
Yes, yes.
Okay, fine. So whether daily climate over a period of time or maybe average of all, and the climate change, how this element itself is changing because of different forces. So let's be clear on that. And so to keep it very elementary, so some of the constituents in the atmosphere, the column of the atmosphere is kind of divided into different regions called as the lowest part of the atmosphere, where the weather is being felt is called troposphere. And a little bit above is more stable column where ozone is kind of very important, it's called stratosphere. And mesosphere, thermosphere, and these are all these atmospheric column and all that are more ionized kind of columnar atmosphere, well widely used for communication and other purposes. And it kind of goes above where the pressure is kind of totally, or the density is kind of totally vanishing. Okay, now let's worry about what is really happening where the weather component is kind of important. And let's only stick to the lowest two parts of the atmospheric column, like troposphere, where the weather is up to 10 to 12 kilometers. You feel the weather components are very important. Stratosphere, generally people refer it to the ozone and other things. Okay. So what are all the constituents present in the, or the gaseous components present in the atmosphere generally? And the majority of the atmospheric column is kind of dominated by the molecular states of nitrogen and oxygen. You can, that kind of encompasses the predominantly the maximum percentage of the atmospheric column. And the remaining, see, if you are going, it's almost like it is almost taken up the whole thing. And the remaining components, it's only very small marginal percentages kind of the atmospheric column is encompassed with the vapor, water, and the vapor of water in the vapor state, and other inert gases in addition to the carbon dioxide, methane, nitrous oxide, monoxide, ozone, and also the chlorofluor. These are all kind of occupying. So it is more like remaining 1%, technically 1%. But even though the percentage is kind of very small, these all gas compounds, they come under the umbrella of greenhouse components. So that is why this kind of differs from the nitrogen and oxygen. So let's get into that. And a simple like this have some kind of radiative properties like absorbing, as well as once we'll get into that. And some of the components that we are seeing here, that is also the concentration keeps on increasing over a period of time. So that also gives more concern. Uh, uh, I mean, like when it is kind of increasing, what is going to be the response, or what is going to be the response in the atmosphere? So that is going to be the question that comes under the ambit of climate change. Okay, let's not totally get into the climate change. These are all important for getting there into climate change. Okay, now let's see the two important components that are very important in the atmosphere. The radiative components, one is kind of scattering. Well, of course, the blue of the sky is coming from the scattering of light. And one is kind of absorbing. So, well, some of the physics people, if they are sitting in the audience, they can assume that anything which is absorbed, it is going to change the electronic state. So that means the absorbed energy is going to be remaining as a thermal energy. So if carbon dioxide absorbs certain incoming electromagnetic radiation, that means it is going to increase the thermal state. Scattering is quite the opposite of that. So absorption by a gaseous compound is going to increase the temperature, whereas the scattering is kind of, so one is kind of giving more forcing into warming the system, the other one is kind of giving more into the cooling the system. And we can see that the list of 1% of the components we have seen, and each gas, it has its own selective absorption bands in the entire electromagnetic spectrum. So let us look into simply like, okay, this is the ultraviolet, which is very important for absorption of ozone in the stratosphere, which is blanketing the which is kind of as a blanket, which serves the, I mean, like for the health and other reasons. Then comes your visible band with all violet to red, all the things that you can visually see, and beyond that it is kind of you can sense. So, and it kind of goes into infrared, far infrared, microwave, and all that. So let's stick to these the visible, I mean, like visible band, or otherwise the bands, the wavelength bands that are before infrared and after infrared. What is the story? So where you can see that this absorption by the components that I showed, like water vapor, carbon dioxide, and ozone or oxygen, and all that, they have some selective characteristics of absorption bands at particular wavelengths. There, the absorptive power is kind of more. For example, your carbon dioxide, it has got, these are all absorption percentage. So maybe around 12 microns and 14 microns and all that. It has got a wide, and you can see that water vapor, it has got multiple. And one more thing that we need to, these are all triatomic molecules. That's why all this I have made it into this 5 to 8 microns. You can see that water vapor here, and 14 microns. You can see that the carbon dioxide has got maximum. Okay, so these are all, these regions are the potentially excellent region for absorbing more. I mean, like the absorbing the electromagnetic radiation by the gas compounds. So carbon dioxide has got anything longer than 12, and water vapor is an excellent one, about 7. Okay, so whenever I'm using the word absorption, that means you are storing some thermal energy. Whenever I'm using the word scattering, which I will not be using more here, because most of the things I'll be using only in the absorption side. Okay, so next one, go into the next slide. Oh, hide captions and highlights.
Sir, down arrow key on the keyboard, sir.
Down arrow, okay. I'm using all the keys. It's kind of frozen. You're sharing, okay. Page up or page down. So nothing is working. Okay. Okay. So where is that sharing? Are you able to still see that? Okay.
It's not in presentation mode.
Okay. So yeah, that's the problem. Once if I'm putting into the presentation mode, it's
So you can use F5, F5.
Okay, 1 minute.
You just
Okay.
press the F5.
Okay, F5 and
Yes, now it's presentation mode.
okay. So no, I'm just checking whether going up and okay now. Uh, okay, now the last slide that I showed. So when you're seeing all these components, the greenhouse components. So there are. I'll come to that eventually. What is that greenhouse effect? So they see that well, they're not showing much absorption in the up to the region where the infrared begins. So the or otherwise you can say ultraviolet. All the wavelengths are very small. It's called the short wavelength. Wavelengths are substantially large. It's called all the infrared kind of falls on the long wave side and visible maybe around 400 to 700 nanometers or anything above 700 nanometers falls in infrared. So you have all the selective absorption band, everything comes in the infrared side. Okay, so the greenhouse has more potential in absorbing the infrared component. That is the point I'm making. So here you can see that they absorb, and as per the radiation theory, the simple 101 of physics of radiation. So anything absorbs as the power of re-emitting back. So any absorber should be a good emitter if it is a black body. That is the fundamental law of radiation. So once it absorbs, well, it can radiate it back. So these are all the components. They absorb as well as re-radiate the infrared, both upward and downward. And the one that kind of comes downward that can warm the surface of the earth. So that is where the global warming or warming of the surface comes in. Okay, now what is happening? Oh, okay, so again, I'm kind of stuck up with this. Sharing. Okay. Okay. So I think page up and page down works better. Okay. Now it's a simple caricature diagram. So the simple logic of I'm going to use the 3 or 4 words here. The reflection, all the physical properties like reflection, absorption, and emission. Okay, let's not worry about the scattering here. That in simple terms. So the incoming radiation coming from the solar or from the sun. Let us assume that 100% of input is this is the part of the atmosphere. Let us assume that this box is wherever the numbers are given. This is the part of the atmosphere where 100% comes in. Part of them is absorbed. Part of them is absorbed by the atmosphere without clouds or maybe other components, other molecular or no, I mean like the substances present in the atmosphere, and so particularly 4%. These are all percentages. So 4% is kind of absorbed, and some of them kind of reflected back also, and by the clouds as well as by the surface. So when you see that this portion, the blue is in the short wave side, and the red is in the infrared side. So when you see that, well, once the energy is kind of absorbed by the surface of the well, the Earth is going to act like a black body, and it is going to emit the radiation back. So these are all emission from the Earth. So that is kind of given. And once the infrared radiation, that also has the same property, like it can partly emitted by the atmosphere upward as well as downward. In addition to that, near the surface, you have all the other components like the heat can be released in the presence of moisture, not in the presence of moisture, such as latent or sensible heat. Some of them, the clouds itself, any cloud drop itself can act like a black body, which has the power to emit. So emission by the cloud, some can be absorbed by the cloud. Some it can be like emitted directly from, I mean, like it doesn't do any work within the atmosphere, but because of the temperature, any temperature of the body, it has the power to emit certain wavelengths in the infrared. So 12% is, so the only point is that 30% is again going back by the solar radiation, and you add up this 49, 58, and 58 plus 12, 70. So if you add up all that, that means the atmosphere is in a very good equilibrium state. So the incoming and the outgoing is kind of balances on the top of the atmosphere. So if these numbers go wrong, like any kind of imbalances come, so something is kind of held up within the column of atmosphere that could warm the atmosphere. That is where the warming and the greenhouse effect comes in. Caption. Huh. So both, I think earlier it was working with the page up and page down. Now, I don't know. Oh, shit. Select content to share. Okay. Okay. Now this, let's go fast. Maybe that once I'm kind of staying in a slide, it is kind of holding up like this. Well, this is not something new. This is kind of known from the Arrhenius days. So he said that by the presence of a carbon dioxide, anything increasing or doubling of the carbon dioxide component can produce as a response. It can respond to the changes in the surface temperature. This was told in 1896, and also by Tyndall. Also, he kind of showed it in a different way about the surface. So, but one thing you have to know that without greenhouse gases, also we cannot live. Only thing, the excess of greenhouse gas only makes the climate change. Let us see that. Okay, so this is a simple caricature of greenhouse gas. Okay, a simple example is that if you just shut down the car and well, the radiation that is kind of trapped in the car, once you put it on a under, not under a shade, put it on an open parking, and after a while during a sunny day you open it, inside it will be kind of too hot. No, I wouldn't say it is warm. Also, it is too hotter than outside. So that is kind of, the heat is kind of trapped inside the car. So the same way, how you can kind of view it in the atmosphere, like, okay, this is the incoming solar radiation, and this blue is kind of the emission of your infrared radiation. The black ones, well, the black ones are already present in the atmosphere in a certain amounts. That kind of serves as a blanket to keep the surface of the one. If they are not there, well, the surface of the surface temperature will be as cold as minus 30 degrees centigrade, which is not livable. So these quantities are really needed to keep the surface of the earth warm to an amount by 15 degrees or 16 degrees, like that. But excess of that, so already I told you that these components is kind of important to keep the surface of the, I mean, like the surface warming to an extent, of the livable extent. But if you are putting more and more extra ones, or all in the brown ones or extra ones, well, it is going to warm too much more. So that is where the simple caricature of this works. Like, this atmosphere is going to be warm, and it is going to be reflected at the surface temperature. Like you expect with the basic components present as a blanket by 15 degrees, that's going to be a little more than that. That depending on the excess amount that we put in that. Okay, now this is the natural greenhouse effect which is needed. So what does it say? Well, you have some natural solar radiation falls, re-radiance. Some part of them, it is kind of re-emitted back to keep the surface warm. And if it in the natural sense, well, more heat has to escape into space. Whereas because of the more greenhouse gases, well, this is going to be more heat is going to be emitted back, and so that less heat is kind of, so the greenhouse component induced by the human is kind of more heat is going to be trapped, and it is going to be re-radiated back to the surface to keep the surface more warming. So without carbon dioxide, all these things, earth would be around 36. With this natural, it will be coming closer to 15 degrees, which we normally see outside. So estimated human activity is going to change by an additional one. I mean, like the more and more we pump in, the more and more it is going to be felt near the surface there. Okay, kind of stuck up with this. The host has turned on the WebEx assistive. Gosh. Okay.
Sir, even on clicking on the slide, it is sometimes changed.
I'm doing all. Okay.
Now this.
Okay. So, and also if you are looking at this other gases like carbon dioxide, methane, nitrous oxide, all those things we talked about, even including the water vapor in the water in the vapor form, that is also going to be a potential absorber of infrared radiation, because all the other gases that we see, this carbon dioxide, they have some kind of a little mixing in nature, or we can say that they mix in the atmosphere very well to remain as in the well mixed state. But water vapor is kind of highly variable. And when you are looking at this carbon dioxide, and the life cycle times is kind of substantially large, or the life cycle of the carbon dioxide can be as high as 200 years. It can go. Methane can go even though smaller. Nitrous oxide, you can see in terms of years. Whereas when you are coming into water vapor, it is kind of in the days. So water vapor is something of a more dangerous element as compared to carbon dioxide. Is fine. It is going to amplify, but it is a slow killer. And the water vapor is kind of a very, very strong absorber that we need to also take into account. Okay, now let's come into that. This is a simple diagram that I have taken it from a manual. See, you carbon dioxide, well, number of percent, you don't worry about this column. So what are all the sources? All the electricity, transportation sectors, they kind of pump a lot of carbon dioxide into the atmosphere. Methane, well, of course, the manure, food decomposite mostly come from that as a source. And nitrous oxide, all vehicle plant emissions and everything. And one more is kind of coming into black carbon, or maybe like a soot particle, like that is. So they are all come in the fire kind of all the. It is also a carbon coated compound or a carbonaceous kind of substance. Well, its life cycle is kind of very small, but its effect of warming the atmosphere could be more dangerous. So, and there is a quantity called greenhouse warming potential that they call it as a GWP. So each gas, what is the greenhouse warming? What is the potential that this gas can contribute to the global warming? So this is kind of taken, this potential is a measure taken with reference to carbon dioxide. So carbon dioxide to carbon dioxide, the ratio is as a ratio with reference to carbon dioxide as a ratio. So when you are seeing that, well, the numbers of others, although this at 1100 years also is kind of a longer time. So you can say that it methane, nitrous oxide, black carbon, as you go into fluorinated, they have substantially larger potential as compared to the carbon dioxide. So this is one thing that we need to. So some of them, like your short lived, like your days to week. This is where the water vapor also comes in. It has got a very short-lived one, but it has got the potential more. Okay, now this is a typical Keeling's graph that anywhere when you open the Google, you will see that how the carbon dioxide concentration evolved right from 1960s onwards when the measurement taken at Mauna Loa, Hawaii. Okay, so you can see that it is kind of having an increased tendency, and we can see that in 1960 it was around 316, as it in 220 it is kind of gone past 400 parts per million. And of course, as on today, yesterday I saw that it has on May 21st, it is still further 4 ppm is kind of more. So what happens here? So let us see that the carbon dioxide has a potential to increase the temperature. Okay, so as you increase the temperature, that is going to increase the potential of your water vapor through evaporation. Okay, so two components are coming here. One, carbon dioxide is contributing to the warming, and it produces water vapor, which is again a greenhouse gas, which is also going to have some kind of feedback to the system. So, which is also going to enhance. So there are some feedbacks also that we need to look into. So if you're looking at, it's a significant gas, in fact, nearly 30 times more effective than, but so we got to know that one can create the other, that can also increase the greenhouse warming much more, or much more significant. Okay, now, so there are some measures. Okay, so we say that temperature, it is having an effect on the temperature, but it is due to the radiation. Okay, so any absorption and other emission, all the properties are radiative components. So in terms of radiation, how much radiational forcing comes, that can create the atmosphere more warmer, or that can create the atmosphere cooler. So there is a measure called radiative forcing. Okay, so this is going to give a measure of the change in energy balance. Okay, so this let's see in this 1951 to 2000, this is a simple diagram. Okay, you can see that the observed warming is in the black. It's kind of around 0.6, 0.7. Okay, so this is, and the component that is kind of contributed by greenhouse gases, it is even much more. And other anthropogenic, or maybe some of the components that can contribute to the cooling side also. Like I said, that absorption leads to warming and the scattering leads to cooling, like your sulfates or nitrates, they have the potential to cool. So the aerosol effects, they mostly they have a component that can contribute to cooling. So if you add up to this, well, this is the combined forcing. So even with the combined forcing, because of the dominance of the greenhouse gases, well, it is maybe around some 0.7, 0.8 it has got. So natural forcings are also coming, as we said, that these are all the anthropogenic or human made. Some natural climate variability forcings are, but they are all nominal. They are all, they don't contribute much into that. So if you are looking at that, GHG, greenhouse gases, potentially warms, and aerosol potentially cools. But the net effect of that totally, if you're combining this, still it is the warming that can give rise to around some 2 or 3 watts. That much power radiative inputs are given to that, that can uh, lead to increased warming. And individual gases, when you are, it's plotted up to 2019. So you see that carbon dioxide has more radiative forcing as compared to CH4 and other things. So, and when you are coming into black carbon, still it has got a warming. Black carbon is kind of black. Anything black is a good absorber, so that's why it's called black carbon. So it is on the positive side. And sulfur dioxide can give rise to sulfates, and they all come in the negative side because they contribute more into the scattering side. Okay, now, so this is a simple diagram like carbon dioxide. Well, this much, this it can raise the temperature by around 0.7. The next is methane and all the other components. There are non-carbon dioxide based components. Even if you add it up, well, it's kind of the big boss is always carbon dioxide. And these are all the anthropogenic kind of things. So organic carbon, ammonia, black carbon. You see that this is the same figure in the reverse form. Okay, now the million dollar question comes, like, what causes? Okay, at the most, climate change is caused by any change in energy balance that I showed it, like at the top of the atmosphere, it has to be balanced. That is in the equilibrium state. When the equilibrium is kind of disturbed, well, anything it is going to, it's more like a perturbation to the atmosphere. The extra radiative forcing is kind of a perturbation. So it is going to respond in its own way. Any system with a perturbation, it is going to respond in its own way. So human activities, large have pumped large quantities of greenhouse. Well, that means the energy balance is going to be influenced. And what are all the consequences that can come once the equilibrium is kind of influenced or affected? Okay, now, so these are all, I mean, like, I will send the PPT for the general reading. So only the takeaway message is the fast fact. Carbon dioxide is the most responsible, greatest by amount till date. So that is kind of one. And the production is 80% of the carbon dioxide production is kind of coming from all the big sectors like electricity, transportation, and industrialization. There is a less than 1% chance that the warming of the atmosphere could be. So this is very clearly, like, from 1950, it is the warming does not come from the natural, only by the man-made. That is kind of a past the fact. Besides all this other emissions that is kind of coming, well, it can come from agriculture, even the land use kind of changing. right from 1950s. So that can alter the amount of incident energy reflecting back to the space. So, well, even agricultural land changing into the constructional land, so that also will be very influential in altering the reflectivity and altering the energy balance. I mean, like the net energy balance. Okay, simple. I'm keeping it very simple. I mean, like not too mathematics or anything. So what are we looking? So there are three components. We know something is forcing. We want to know what is the response, how much the forcing is sensitive to the response. So these are all the three quantities I'm taking it. And I'm just giving you a general picture. Let's see that there is a climate forcing. Well, so there is a change in the radiation balance at the top of the atmosphere. Let us assume that a small incremental quantity. And what is the response? Well, it is going to respond to the surface temperature. So if there is a small change, how much change is going to come? So if we are equating, well, like a simple linear kind of equation, if you are taking the what is the change in the surface temperature to the change in the forcing, this is going to give rise to, okay, it is going to form into as a response function. Okay, so delta Ts, a small change to that, it is a proportional cost. So the magic lies how to quantify this. That is what all the climate scientists are breaking, especially when you want to address how much climate change. Okay, whether tomorrow, a few days ago, a rain event came. Is it due to climate change? So we need to address like how we can quantify this. It's not that simple. As I have shown here, it is kind of in a simple way, but it is not that simple. Okay, so just only a simple parameter that I am taking, changes in the surface temperature is going to affect the long wave radiation, because the earth is going to act like a black body. And also if the changes on the surface could be an icy surface or snowy surface, or maybe the atmosphere contains some cloud, so it is going to alter the reflectivity. And if the atmosphere present with the water vapor, well, that is also going to absorb the long wave that is kind of coming. So the change in this one, well, the change in your outgoing long wave radiation, the change in the albedo, and of course the incoming solar radiation also, it's going to change the solar inputs. So once the temperature is kind of changing to a certain extent, it is going to produce more water vapor, because through evaporative processes, water vapor can again influence the temperature by absorbing more. So this way, like what are all the things that is kind of influencing the system to identify how much change in the surface temperature can be obtained. That is the magic of all the. I'm keeping it very simple, but it's not that simple or straightforward. Now, let's get into this simple logic into this, like if water vapor presence in the atmosphere, well, whether it can feed it back or enhance the warming process. If you call that, oh, the presence of water vapor, like I said, that carbon dioxide can increase the temperature. Once the temperature increases, obviously, water vapor, the evaporation is going to produce more water vapor. Both are greenhouse gases. Both are going to absorb the infrared radiation and re-radiate back. So this is going to be like there is one feedback process. So the global warming process is going to be amplified. So if it is the process is going to be amplified, we call that as a positive feedback. If it is not amplified, we call that as a negative feedback. So here is a simple one. I can say the climate warming, it is going to increase the atmospheric vapor and it is going to trap more radiation. Obviously, it is going to increase the warming. So the cycle is potentially, increasing. So we call that as a positive. The response is kind of amplified. It is given in the black one. Response is kind of this one, it will be in the negative. So again, if you are seeing in the ice, okay, so ice melts by the global warming. Warmer temperature can melt the ice sheet. So it is going to reduce your the reflectivity. The ice has got the highest reflectivity surface. So if ice reduces that, well, then it is going to alter the system. So like that, if you are listing it, so there's some of the feedbacks, but how to quantify that one that I showed, the lambda based on this feedback, that is the magic of the system. Magic, that is the, oh, Okay. Okay. So when we are seeing that, well, that is what is, I mean, and coming to this, if you are saying that clouds itself, as I said, that cloud, the drops that present that can act like a black body. So still, clouds also can play a bigger role. However, the other feedback mechanisms, at least quantitatively, we can estimate through certain assumptions and certain mathematical evaluation. But this cloud one is a very complex process that I mean, like it poses more as compared to the others, it poses more uncertainties in the estimate. So the feedback effects come, well, it is going to give the magnitude of your climate change through all the feedbacks and transient response, well, how much ocean is uptaking, how much it is kind of contributing to the circulation changes, pattern, well, land hydrology, vegetation feedback, and of course, it is going to also influence like your natural, if the climate is changing, well, the natural variable elements are also can be influenced by that to certain changes. And and there are different cloud types respond to the climate change in a different way. When you are taking a low level cloud, maybe within the boundary layer, if you are taking it, low level cloud or stratus or a foggy kind of layer, if you are taking, that is a potential influence of cooling. It more like an umbrella kind of thing. It cools the incoming radiation that falls on that. It more of them will be reflected back so that the surface is not going to be warmed by the influence of that. At the same time, these clouds have more potential in increasing the thermal emission because of the water and the drops that are contained, depending on the optical depth of this. So more emission is kind of going more. So it is kind of going to keep your surface more cooler. So it is contributing to a cooling side. Whereas when you are taking the upper level clouds such as cirrus or anything, right, the quite opposite comes here. It has more potential of warming the atmosphere. So different, how estimating the low clouds itself is from the, because we don't have nowadays the satellite measurements have come, but models are also used, but the models have to produce the distinction between these two clouds to estimate this. So still the cloud radiation feedback is kind of still remains more uncertain. Oh, oh, okay. Next. Okay. Now let's go get into that. What is the current state? I have taken all this from the assessment report recently released from the IPCC. Okay. So it's kind of clearly mentioned that the human influence of the climate is kind of nobody can deny it, or they say unequivocal. Okay, so when you say that the carbon dioxide concentration and prior to the industrial times, these are all probably they might have estimated through all the paleoclimatic records. So when you are looking at only this century's beginning from the industrial 1870 or 1850 onwards to the present 2020, well, it has got very slow increase up to 1970, and then from 1970 onwards, it is kind of showing a very sharp rise. It's not only shown in carbon dioxide; it is kind of shown in the other greenhouse gases also about the same time of 90, maybe because of more industrialization, more changes in the system, and all that. So, in the 2019, the amount was around some 410 and 1866 parts per billion, like that. And the current estimate is, you can see that around within 3 years, this is about some 11 parts per million, around 2%. So the rate at which the carbon dioxide, the increase, when you are seeing, it's about roughly about 1 to 2%. So we are kind of witnessing. And when you are seeing for different gases, what is the radiative kind of forcing comes? So if you take greenhouse, so this is your carbon dioxide, it has got the maximum forcing. And the other one, if you are taking methane and other things and all, they are all at the positive side. So that means positive radiative forcing is going to make the warming of the system. Well, of course, when you are taking the aerosols and all that, potentially they tend to cool the system. Okay, so when you are looking at the warming side is more dominated by the cooling side. Okay, so even when you are saying that, how much is the changes in the radiative forcing when you are seeing it? Well, from 1950 onwards, well, it is also showing a certain positive increase in the anthropogenic effective radiative forcing. It is also showing certain slopy surface that had certain changes in that. Okay, so This is very clear. Unequal, stable climate, incoming and the outgoing should be even. Well, if it is not even, that means it isn't fully balanced. And if there is an imbalance, well, the imbalance is going to cause it is going to cause the changes within the system. Well, the one thing which you can directly see it, well, you can easily notice it on the surface temperature. But as a whole, in the entire atmosphere, it is going to change. Okay, next. Okay, now changes when you're saying that, well, people talk one aspect you can talk as a global, one aspect you can talk as regional. So if one changes, how it is kind of modulating others to result into us. So it is not a straightforward path, like if one the surface temperature is kind of changing, how it is going to be influenced by that. So if you're saying ocean, well, sea level, it is influencing, increasing, sea surface temperature is increasing, well, ocean heat content is also increasing. At the same time, ocean acidification. We see ocean is a good sink of the carbon reservoir. But unfortunately, well, it is a good news for greenhouse warming that it is going to, I mean, it is going to act as a sink. But at the same time, it is going to increase your pH and other chemical quantities and acidification. So that is also one positive side is there, one negative side is there. And ice, well, ice is going to melt. Arctic ice sheet cover is kind of melting the area around Greenland and all that. You can see that and glaciers are melting, retreating. Snow cover is also falling down. This is over ice. And what is happening in the atmosphere? Well, air temperature increases. Obviously, it is going to modulate on the circulation because air temperature, water vapor is increasing. Surface temperature is increasing because of the greenhouse effect. It can influence the atmospheric circulation. It can manifest on the changes in the atmospheric circulation. So you can see that it can manifest. Looking at the temperature, how it is kind of changing over a period. And we can see that this is the industrial to present. When you are seeing that from 1970 onwards, the rate at which it has gone, the surface temperature has come up to maybe a little bit over 1.1. It is kind of warm. Okay, so the observations, you can see that global. Okay, so you can see that around 1.1. And what are all the contribution? It is kind of attribute. This attribution studies itself is very, whether it is due to a particular carbon dioxide or methane or this one. Some of the studies they kind of attribute. They say that okay, the carbon dioxide guy is a big guy, and the greenhouse warming is given more potential to the rise in temperature. Whereas the aerosol cooling is also the addition of this combination of this, but still in the aerosol cooling side, all the cooling side. Globally speaking, well, it is kind of the plus and minus. It is kind of giving as a plus, but we don't know that in the regional side when you are taking this could be smaller, this could be more, or they could be even also. That some studies are there, like certain regions, if you are seeing that the greenhouse effect kind of counteract with the aerosol cooling, or aerosol could be more dominating than the the greenhouse warming, things like that. So generally now from a global perspective, the human influence really is kind of causing the temperature rise of 1.1 degree warmer. And improved understanding on the this is again an area that independently how much carbon dioxide is potentially component. Evidence from these are all from sensitivity examination, that the sensitivity factor that I described before, like the carbon dioxide has given a component up to uh, a little bit over zero point 0.7, and methane, these are all potential one, they are kind of giving maximum as compared to the other other components. Okay, now it is very clear that widespread changes, well, human anthropogenic kind of induced, it is kind of changing. So the red is kind of changing in the positive side, whereas the contribution to where it is kind of contribute, air temperature rise, it is going to contribute to water vapor rise, which is going to contribute the air temperature in the lows. Well, of course, the greenhouse is increasing, it can contribute to more water vapor, it can kind of change the atmospheric circulation like that. This is kind of having a this a little caricature kind of says about like what is driving, what is the consequence. And now when you are seeing that, well, so far the global picture you have seen that, now it is when you are seeing that whether it is uniformly happening everywhere. So when you see that Africa, when you are seeing it, you can see that human caused and natural. Okay, this is a natural variability alone, and one experiment is conducted with the natural, and one experiment is conducted with the combined. And the dark line is the, I think, the actual data set, that observed data set. When you're seeing that human caused and the natural combined, it is kind of showing the more realism. But when you are saying that in Africa, or take different continents, everywhere it is kind of showing it is kind of more uniform. So maybe the amount of the temperature change could be different, but the rising temperature is kind of more uniform. So it is already affecting every in many different ways. And this is one point I wanted to make. And the newspaper guys always say, I mean, like I used to receive a call uh, that, okay, the event has occurred, it was very severe, so many things happened, flood has come. Well, is it due to climate change? So if they pose, well, it could be due to climate change, but it is kind of, it may be a sign of that, but we only one event attributing to climate change is, it's not the way one has to go. So higher frequency of certain similar events occurring, then only we can club together, well, climate is kind of responding, or climate change is kind of as a response, not a single event. Okay, and what are all the risks that that climate change can pose? Well, these are all some of the examples that you are witnessing: a heavy flood or heavy rain that poses, and wildfire recently. Recently, 1 minute. Hello? नहीं, अभी नहीं, वो IMD का था. And ice sheet is melting. And there was a international disaster database that I could see that, well, only the high impact events globally, when you are seeing that, well, after 1970, you see that there is kind of a little rising trend. Of course, it is kind of showing a little falling, but so after that only the influence is kind of more dominated when the temperature starts in going on the uphill trend. 1 minute. Next. Okay. Now, the other question, simple question comes, okay, climate change, I believe it, but who is really creating it? That is another question that it might come from that. So when you are looking at in general, well, the more developing countries in the West are the biggest producers. Okay, while the least producers are the influencing. I mean, like we are most affected side. That is what the point is. See, you can see Africa, you can see South America, the ocean regions. Another, the contribution is kind of, as Asia, of course, it is a very big region as compared to Europe or North America. So we cannot go by the just by the pie chart. But in general, the USA and EU and the China alone have contributed to more about 60%. The countries who have contributed the least, we kind of people are having more climate crisis. Ooh, is this a fair, I mean, fair deal? That is the kind that I pose here. Okay, why is climate change problem? Is can cause 5 critical changes: warming, surface and the oceans, and it can alter the precipitation patterns and water cycle around it. And of course, it can retreat. It can melt the glaciers and snowpack. It can force, or the manifestations can come on the sea level rise, as well as the good news and bad news can come on the ocean side also. Okay, now the question comes is that, well, so far the current state of the climate is known. So what is the possible climate that we can expect in the future on the rest of the century? Okay, so there are some numerical experiments or maybe model experiments are conducted with certain planned scenarios like, well, if we are increasing the carbon dioxide or the greenhouse concentration, and if you are containing or if you are mitigating the so different scenarios are kind of constructed based on this judgment, and they came up with around some 5 different pathways if the concentration proceeds, how the climate, or that is why I use the word possible. This is a possible scenario. If there is a possible scenario like this, okay, so that, and this is the carbon dioxide concentration in a gigaton per year. So if you are going in this way, what is the response it is going to be having at the temperature, and what is going to be the responses on not just only the temperature, in other aspects also. So there are some relevant this is it is actually, it is not only the scientists participated in the policy makers and everybody, they kind of came up with that, like there should be a very high possible scenario and a moderately high and intermediate, and if you are going in a very low, so they kind of made this in such a way that if the carbon dioxide goes in different pathways, what is going to be the resultant outcome of climate. So this is called as a shared socio-economic pathways. Earlier it was called representative concentration pathways. Okay, so this, like if we are putting more energy, like in terms of radiative forcing itself, like by varying, like if you are putting two, see these numbers when you are seeing it, like if you are heading towards a radiative forcing of 8.5, if you're heading towards a radiative 7, 4.5 or 5, then these are all the numbers. Like if we are heading towards that path, what is going to be the resultant outcome in that? So this that is called as SSP pathways, 1, 2, 3, like that, depending on the numbers here. Okay, so one is on the indicator of warming, because of the radiative forcing is kind of more radiative forcing, positive one, it is going to be more warming. One is kind of on the mitigation side, like if you are traveling a path in the opposite sense. And of course, if you want to look at it in not in the not in the radiative forcing way, well, you can still look at it in the simple logic of concentrational pathway. Like if this very high, it is going to be more than 1,000 parts per at the end of century. And if you are taking intermediate, maybe one half of that, around 550. So if the concentrations reach around 550 parts per million of carbon dioxide at the end of the century, what is going to be the scenario? What is going to be the climate scenario? So this is one that the current the climate community is kind of looking for. Okay, so now, well, the global warming, well, so we expect reductions of carbon dioxide. That is, if you are seeing that, well, some scenarios you keep on increasing it and then kind of expect some, well, don't give the mitigation at the end of the century, and don't give the mitigation but keeps on increasing. So these are all, and some kind of, some regions may produce more, some regions may not produce more, they may not come into some kind of agreement. So they are all coming into that as different names. Like if you take a middle of the road, that intermediate one, very sustainable, like if we agree to keep the carbon reduction or agree to keep the carbon dioxide much below, or we don't want to agree, so there will be a rivalry, like one country will say that we cannot stop it, one other country will. So this kind of things. So if we are looking at that, and now, so let us see that this is kind of scenario, like if we are heading towards at the end of the century with a temperature increase of 1.5 or 2 degrees and 4 degrees, what is going to be its response in the annual precipitation? You can clearly see the response is kind of the colorfully, it is kind of, as you go higher and higher, well, the color is going to be much, much worse. So some wet regions are becoming more and more wetter, and the dry regions are becoming more drier and drier. This kind of scenario is kind of emerging. And when you are looking at, okay, now you will ask that what is the story with our region? Okay, so this is also taken from a recent assessment that was assessed on the climate change pertinent to the Indian region. So when you are seeing that, well, this central portion, change in the air temperature, when you change in the precipitation, when you are seeing at different representative concentration pathways. So if you are taking 4.5, that means at the end of the century, if the carbon dioxide touches 550 parts per billion, at 8.5 means it touches more than 1,000 parts per billion. So if you are expecting that in the immediate around up to 20 or middle part of the century, you can expect that the ranges can go a little bit higher, like as 11 the 11 percentage increase. And when you are going with a high concentration input, well, it is kind of nearly doubling, nearly it is kind of increasing. And the surface temperatures also can go as high as around 5 degrees. Well, if we are taking a path of the highest emission scenario, we are taking a path of a lowest emission scenario, still it can be anywhere about 2 degrees. And also this is just only the temperature and precipitation. It has consequences in others. So you can see that there can be a rise in the tropical cyclones formation, and the intensity can be in the northern Indian Ocean basin. Also, when you are seeing that monsoon low pressure system activity can pose a poleward shift, then so this is also, these scenarios exhibit some kind of symptoms like this, and enhance heavy rainfall occurrence. However, well, we don't have enough studies to consolidate to say something very authentic. So the confidence is kind of somewhere in the middle. So it is better to believe it and totally not believe it. That kind of confidence is called as the medium one. Okay, now I'm coming to an end. Continued global warming is projected to intensify. It is going to influence more on the water cycle and also the variability, particularly in the global monsoon precipitation. I showed that the months, if you are looking at this, see, this is our monsoon region. And when you are looking at Sahel and this region, it's kind of enhanced precipitation with the increase. Whereas when you are looking at the North American monsoon, okay, it is kind of getting more drier and drier. So it can influence the monsoon in different ways. And severity of wet and dry events, like you see, a few days ago, you saw that the Europe is kind of having the highest possible temperature in the UK, and also heat wave kind of persistence. Okay, so these kind of events, it can become more severe, and the number of events also can be more, as well as the severity of the events also could be so fell. So these are all the potential possible things that way, the more heat waves, heavy precipitation, that is kind of a rough estimate, like if 1 degree rise goes around 7% rise in the annual precipitation that can come into that, and droughts and intense tropical cyclone, they are all projected, like in the next in this 21st century, that they are all projected to be larger. And also the tropical cyclones are not going to be the conventional type, but it's going to be have more intense ones. Okay, with every increase in the temperature by global warming. Okay, so I have come to the last one. Uh, so how to go about it? So we need to go for some sustainable and non-polluting kind of. So how possible is that as the population is also increasing, and we expect by 2050 to 9 to 10 billion population. So more population, more energy demand, more production. So how we can contain it? That is a big question. Like how best we can go about it to mitigate the carbon sources at the same time. Are there any kind of alternative resources that can kind of contain the carbon production? So this is kind of, so the fossil fuel is highly dominated in the world, whether that can be used or not sustainable. Combustion is kind of a constituent for air pollution. If you want to contain this, the fossil fuel consumption has to be contained. So we have to go for some kind of alternative renewable kind of energy resources. That could be, or how best we can go about it. Renewable, we cannot just immediately overnight we can do that, but that is one possible pathway to contain that. I believe this is my last slide. I can take up questions.
Audience can ask a few questions or whatever questions they may ask.
And well, this I will send it to you. If the audience wants the PDF copy of this presentation, they can use it. I'm openly if they want, really.
Yes, sir. Yes, sir.
I'll
We'll
send it
share
to
it
you.
with the audience.
You can share it.
Yes, sir. So, any questions, please?
It's already 4:30 maybe. I hope the audience didn't sleep.
Yeah,
Yes,
excuse
sir.
me, sir. May I ask the question?
Yeah, sure. Go ahead.
Yeah, sir. In one of the slide, it was mentioned that agriculture also contribute to the climate changes. Like something like that, it was there. So,
Yeah,
can you?
agricultural. Well, see, yes, uh, the agricultural farms. One of the producers of manure is there. Okay, that is going to be the source for your methane. Okay, so when agriculture comes, well, the carbon dioxide survival is also going to be depending on deforestation and things like that. It is a wide component used in the transpiration also. Okay, so any changes in the agricultural setup is also going to alter the concentrational setup. That is what the meaning I just took.
So, in the ultimate sense, so it is anthropogenic only. It is not like
Well,
in
who is
the.
going to reduce the agricultural farmlands? Only we.
Yeah, yeah, yeah,
Although it is anthropogenic.
yeah. So, as such, agriculture is not like a contributor to the climate changes.
No, 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 no. You see, there could be an active one. See, if the agricultural lands, okay, the more and more greenery, well, the more and more it is going to act as a carbon sink. Correct? It is because the plants suck the carbon dioxide and releases oxygen. So more and more greenery, it is going to be reducing your carbon dioxide. But if you are making those agricultural farmlands and all that into a different one, you cut down everything and change it. Obviously, your sink is going to be influenced by that. So source is going to dominate after that.
Yeah, in that sense, yeah.
Sir, you can unshare your presentation, sir.
Excuse me?
Unshare the presentation more.
Yeah. I will send it to the organizers and they will share it with you. The
Stop
PDF
sharing
doc.
now. Stop sharing.
Stop
I
sharing,
don't
sir.
know. I mean, like I here itself. Can you download it, or I don't know how it works.
No, sir. Stop sharing the presentation. Stop
Okay,
sharing
okay,
presentation.
okay. Oh, good.
Okay. Now.
Okay, I thank Dr. Ramesh Vellore for his excellent and very short, means very good lecture, and very to the basic. He has explained what is the difference between weather, climate, and climate change, and all the other things about that. So I thank once again to him for the good lecture, and I appeal to the audience. They can anytime contact him on his email ID or through us, or
Most welcome.
feel free to all your queries. He will be very happy to associate with you. Okay.
You're most welcome. So can I turn that, because maybe the next speaker will be online? Okay, I'll send it to Gauri, and you will send the PDF documents to you. Okay.